Okay, in this video I'm going to be talking about the linearization of nonlinear relationships uh, related to curve fitting or regression in the least square sense. So in the previous video I talked about simple linear regression. So simple linear regression. So if we have some data set, one-dimensional data set, some function of x, and we have some data points, and it looks like the relationship is linear. Well, what we like to do in the simple linear regression case is fit a line to that data that minimizes the sum squared error. So our model here is maybe this data, we call it a set of xi, yi. That's these data points right here. And then we want to fit a model, which is the equation for this line right here. And the equation for that line, we can write it in general terms as, I'm just going to write it as w sub x is equal to a naught plus a1 times x, where a naught and a1 here, these are the model parameters. So in order to find the best line, we need to find the parameters a naught and a1 that define that line that minimize the sum squared error. So what we did was we defined the sum squared error. Sum squared error was equal to the summation over all our data points from I equals 1 to n, so where we've got n data points of our actual data, yi, that's this data right here, minus w at xi squared. So we found the best a naught and a1 by minimizing SR with respect to a naught and a1. Alright, so to do that we took partial derivatives of SR, partial derivative of SR with respect to a naught, set that equal to 0, solve for, and then we also took the partial derivative of SR with respect to a1, set that equal to 0, and that gave us two equations in which we solved for the best a naught and a1. That's how we minimized the sum squared error. Now, this video isn't about simple linear regression. I just wanted to give you an overview of simple linear regression because we can use simple linear regression with nonlinear relationships so long as those linear relationships can be linearized. So what if we have some data that instead of looking linear, maybe it looks like some kind of power law. Okay, so x and y, and maybe the trend of our data, so looks here, maybe the trend looks something like this, some form of power law or exponential. So our data might look something like this. Okay. This is obviously a nonlinear trend, but if we have a model that's going to predict this red curve, that model might take some form like this, some parameter A times x raised to another parameter b. This is called a power law relationship. Power law. Maybe we have another form that's linearizable. So this can actually, this form right here can be made linear just by a transformation of variables. And so can other nonlinear relationships. So like the exponential. So if I have some parameter a times e raised to the b times x, this is exponential. The exponential relationship. There's many others, but like hyperbolic. Hyperbolic looks something like this. This is linearizable. A plus b over x. And so these equation forms can be converted to linear equations. And that's what I mean by linearization. So let's just write that down. So these equation forms can be converted to linear forms. So let's, and that process is called linearization. Okay, so let's talk about linearization. Linearization. All right, so let's just take the power law as an example, and I'll show you how to do it. So taking power law, y equals some parameter a times x raised to another parameter b. So when I say parameter, I mean we could put any numbers in here. Alright, it's a model. Depending on how we change the parameters, the curve that we're fitting to the data will change. So maybe one set of parameters is going to give a curve like this. Another one's going to give a curve like this. Another one's going to give a curve like this. Maybe not like that. But we got all different shapes of curves that are defined by these different sets of parameters a and b. Okay? So the power law, the way that we linearize it is we can take the natural log of both sides. So let's take the natural log of both sides. When we do that, we get the natural log of y is equal to the natural log of a times x raised to the b. Now, using rules of logarithms, properties of logarithms, we know that the natural log of the product of two things, so if I have m times n, that's just equal to the natural log of m plus the natural log of n. So we can apply that here, and we can break this up and say this is equal to the natural log of a plus the natural log of x raised to the b. Now there's also another property of logarithms, of exponents and logarithms, such that we can say the natural log of x raised to the b is just equal to b times the natural log of x. So taking that into account here, we can come up with our final equation. Ln of y is equal to the natural log of a plus b times the natural log of x. Alright, now this equation probably doesn't look linear to you, but it really is. So if I take and I define a new variable, y prime is equal to the natural log of y, and I say x prime is equal to the natural log of x, I can make these substitutions up here. I'm also going to define a naught to be equal to the natural log of a, and a1 equal to b. Okay, so now with these new relationships, I'm just going to make substitutions in. So here I get y prime, because that's just y prime is the natural log of y, is equal to, here I've got the ln of a. Well, I said the ln of a is equal to a naught right here, so this becomes a naught, plus b I'm calling a1, and then the ln of x I said was equal to x prime, so this becomes x prime. Well, these are just new variables, but this right here is the equation for a line, right? If I plot these variables as x prime and y prime, this is some line in that space where these variables are a naught, where it has a slope, y-intercept of a naught, and slope of a1. Right? So really, I started with this power law relationship up here. Here's the power law relationship, and I converted it just using a transformation of variables to a linear form. So how is this useful in the curve fitting sense? Well, if I have some data, so let's say I have some data, and it is like this, so maybe it's okay. It doesn't really look linear. I mean, we could fit a line to it, but it's just not a very good fit. So what we might want to do is do some sort of power law. It looks like a better fit, something that's kind of nonlinear. This is like a power law fit. Well, if we wanted to do that, what we could do is step one is to transform our xi, yi data to x prime I, comma yi prime data, using the relations that we talked about, using x prime equals, we could say xi prime is equal to the natural log of xi, and yi prime is equal to the natural log of our yi data. Okay, so if we did that, what we would find is, hey, when I transform my data like that, all of a sudden the data goes from looking like it did up here to looking something like this. It got, when we did the transformation, it became more linear. Okay, so now we can fit a line to this and it fits real nice. Well, now these axes aren't y and x, they're x prime and y prime, right? Because we're plotting the x prime and y prime data. So all we do is we fit a line. So fit line to transform data. Which we know how to do. I have a video on simple linear regression. So this is kind of step 2. Step 2 is fit a line to the transform data. And then let's say, okay, well that's great and all. Now I've got a line that fits this transform data, but really what I wanted to begin with was I wanted to figure out what my parameters were for my power law. So let's just rewrite it down here. So you could say, well, what I really want to know is I want to fit a curve y equals some parameter a times x raised to the b, to the original data, to the yi data and the xi data. Well, that's not a problem. Once I fit this line, I can calculate what my a and b parameters are using the relationships that we derived when we did the linearization. Remember, we said that a1, a naught was equal to the natural log of a, or this a right here, okay? And then we said a1 was just equal to b. Okay, well we want to know what a is and we want to know what b is. Well, b is just a1, right? It's just the slope of this line. So that's easy because we figure that out when we fit the curve to the line. But a naught, we can just we can solve for a in this equation and we get a is equal to the exponential of a naught. So we just exponentiate the slope, the y-intercept of our fitted line right here, and that gives us a. Now we can plug those parameters back into a model, and with our original xy data, so now instead of y prime and x prime, our original data, which is nonlinear, so now remember we wanted the curve that looked like a power law, a true power law. Okay, well we can do that because we've calculated a1 and b, and so now we have the equation for this line, which is just y equals a x raised to b. Alright, so that's kind of step 3. Let's summarize all the steps down here again. Summary of steps. Alright, so first step in linearization is to transform the xi, yi data using the appropriate transformation for your nonlinear form. Nonlinear model. So for power law, you'd use the natural logs that we talked about, and I'll put up a table here that shows a list of all the forms. But the second step is once you've transformed the data, then you want to do linear regression. Okay, hold on. So transform the xi, yi data using the appropriate transformation for your nonlinear model. Let's put down here to get xi prime, yi prime linear data. So it makes the data linear, okay? Second step is fit line to linearized data. Xi prime, yi prime. And then last step is to transform A0 and A1 back to nonlinear parameters, nonlinear model parameters. All right, so let's just kind of zoom out here. So those are the basic 3 steps. Let me see if I can pull up a slide here showing all the linearizable forms. All right. Here's a list of the non-linearizable forms. So we've got hyperbolic. It shows you in this table kind of the name of the form. So hyperbolic, exponential, exponential inverse, power law, saturation, and these are what the forms actually look like. So this is kind of what the hyperbolic form looks like, the exponential form, exponential inverse form, power law form, saturation form. And then it shows you the transformations that you apply in order to get x prime and y prime that make it linear. So for the hyperbolic, to get x prime, you take 1 over x, and y you just leave the same. And for the exponential, x prime is equal to x and y prime is equal to the natural log of y. So you see this, and then it also shows you here the parameters. Okay, these we're assuming are the parameters for the line A and B. So if you want to get back to your nonlinear parameter, which we're calling A prime and B prime, no, sorry, A prime and B prime are the linear parameters that I called A naught and A1. So that's A prime and B prime. And A and B are the parameters for our nonlinear forms or models. Okay. Anyways, so you can see that if you want to get A and B for the power law, like we said, you got to take the exponential of A naught, which is called A prime in this table, and B was just equal to B prime, which was, sorry, this was A1 and this was A naught. No, A naught and this was A1. Yeah. Okay. Anyways, that's the list of tables. In another video, I'll go ahead and do an example in Excel of how you can do this. But for now, I'm just going to stop here, and I'll talk about that in another video.